Hold out your hand. Go on, seriously. Do it right now. Now, imagine that hand in sunlight. Feel the warmth. That warmth is coming from a nuclear furnace 93 million miles away. And with that warmth comes something else. Something invisible. Every single second, from the sun alone, 100 trillion invisible bullets are tearing through the space your hand occupies. They aren't stopping. They're passing through your skin, your muscle, your bone, and out the other side as if you are completely transparent. As if you are a ghost. But they are the ghosts. They are particles called neutrinos. And these ghosts, they might be the only reason you exist at all. Because 13.8 billion years ago, the universe began with a rule. A rule of perfect balance. In the unimaginable heat of the Big Bang, for every single particle of matter created, an equal and opposite antiparticle was also born. The ledger was perfectly balanced. And when matter meets antimatter, they annihilate. They turn into pure light. That's the rule. So the newborn universe should have been a brief, brilliant flash. A cosmic bonfire where everything cancelled everything else out, leaving behind a vast, empty, silent cosmos filled with nothing but cooling radiation. But you are here. Your hand is solid. Your thoughts are real. We are the impossible survivors. So, something cheated. The cosmic ledger was tampered with. Today, we open the case file on the greatest crime in history, the survival of matter. We're going to audit the evidence, follow the clues, and build a case that this nearly nothing particle, this cosmic ghost, tilted the entire universe in favor of you. Our investigation begins, as all good detective stories do, at a crime scene. The time is the 1920s. The location, inside the nucleus of an atom. Physicists, the detectives of reality, were studying a seemingly simple event called beta decay. This is when a neutron, a neutral particle in an atom's core, spontaneously decides to change its identity. It transforms into a proton, which has a positive charge, and to balance the charge, it spits out an electron, which is negative. Simple enough. But there was a problem. A huge one. One of the most sacred laws of physics, a law as fundamental as gravity, was being violated. That law is the conservation of energy. It states that energy cannot be created or destroyed, only transferred. When a firecracker explodes, the chemical energy in the powder is converted perfectly into heat, light, and sound. Nothing is lost. When a pool ball hits another, the energy of the first ball is transferred perfectly to the second. The books always balance. But in beta decay, they didn't. The detectives would measure the energy of the nucleus before the decay, and the combined energy of the proton and electron after. And every single time, some energy was missing. Vanished into thin air. It was like watching someone put a $100 bill into a sealed box, shaking it, and when you opened it, there was only $80 inside. Not 99, not 85. A random amount was just gone. This wasn't a small problem. It was a reality-breaking crisis. Some of the greatest minds, including the legendary Niels Bohr, were ready to throw out the law of energy conservation itself. They were willing to believe that at the quantum level, the universe was just leaky. That energy could just blink out of existence. Into this crisis steps our first hero, the brilliant, famously critical, and deeply cautious physicist Wolfgang Pauli. Pauli hated sloppy ideas. He was a purist. And the idea of abandoning energy conservation felt like an act of desperation. He had another idea. An idea so wild, so seemingly untestable, he thought it was scientific heresy. In December of 1930, he couldn't attend a physics conference, so he wrote a letter instead. He addressed it famously to the dear radioactive ladies and gentlemen, and in it, he confessed his sin. He wrote, "I have done a terrible thing, I have postulated a particle that cannot be detected." He said he had found a desperate remedy to save the laws of physics. His remedy? There wasn't a crime against physics. There was a thief. He proposed that in every beta decay, a third, unseen particle was being created. A tiny, neutral, lightweight accomplice that was stealing the missing energy and escaping the crime scene completely undetected. A perfect phantom. The idea was so radical that for years, it was mostly a private joke among physicists. But it caught the attention of the Italian genius, Enrico Fermi. Fermi wasn't just a theorist, he was a builder. He took Pauli's ghost and gave it a rulebook. He developed the mathematical theory of how this particle would operate. And he gave it its name. In Italian, a neutron is a neutron, a big neutral one. So Fermi, with a bit of poetic flair, called this new, tiny, neutral particle the neutrino. The little neutral one. For the next quarter of a century, The neutrino was just that, a ghost in the equations. It made the math work, but there was zero physical evidence for it. It was a convenient fiction. But science isn't about convenience. It's about proof. So let me ask the question that obsessed physicists for 25 years. How in the name of the cosmos do you catch a ghost? You don't build a better camera. You build a better trap. In 1956, two incredibly patient and clever American physicists, Clyde Cowan and Frederick Reynes, decided to do just that. They needed a place where the suspect would be found in overwhelming numbers. So they went to the Savannah River plant in South Carolina, the site of a massive nuclear reactor built to produce plutonium for weapons. A nuclear reactor is, for our purposes, a fire hose of neutrinos. It spews out more than 10 trillion of them, per second, for every square centimeter. They set up their ghost trap nearby. It consisted of two huge tanks of water, containing about 400 liters, with a special chemical, cadmium chloride, dissolved in it. Here was the genius of the trap. According to Fermi's theory, if a neutrino, or technically an antineutrino from the reactor, were to hit a proton in the water, it would trigger a specific, two-step reaction. Step 1, the antineutrino hits the proton, turning it into a neutron and creating a positron, an anti-electron. That positron would immediately find an electron in the water, and they would annihilate, producing two distinctive flashes of gamma-ray light. That's the first signal. Flash. Step 2, the newly created neutron would bounce around for a few millionths of a second until it was captured by one of the cadmium atoms. This capture would cause the cadmium nucleus to get overexcited and release another, different flash of gamma rays. That's the second signal. Flash. This two-flash signature, separated by a precise, tiny delay, was the fingerprint. It was the only way to be sure they had caught a neutrino, and not just some random background radiation. They turned on their detectors. They waited. For months, they sifted through the noise. And then, seeing about 3 of these double-flash events per hour, they had it. The signal was clear. Unmistakable. They sent a telegram to Wolfgang Pauli. He was in Zurich, at a conference. He received the message, read it to the audience, and that evening, he and his friends opened a case of champagne. After 25 years in hiding, the ghost was real. The suspect was finally in custody. But like any good mystery, identifying the suspect was just the beginning. Now the detectives had to interrogate it. And the more they studied the neutrino, the stranger, more alien, and more important it became. The first thing they confirmed was its incredible antisocial nature. Why was it so hard to detect? Because it barely feels anything. Of the 4 fundamental forces of nature, it completely ignores 2 of them: the strong nuclear force that holds nuclei together, and electromagnetism, the force responsible for light, magnets, and all of chemistry. It's not just that it doesn't like those forces, it's that to a neutrino, they do not exist. It does feel gravity, but because its mass is so tiny, gravity's effect is almost zero. That leaves only one way for a neutrino to talk to the rest of the universe: the weak nuclear force. The weak force is the force of change. It's responsible for the radioactive decay that makes things like carbon dating possible. It's the engine that powers the sun, by turning protons into neutrons. And the weak force, well, it's a weirdo. It has a secret, fundamental prejudice. It's left-handed. This is one of the most profound and bizarre facts about our universe, so let's unpack it. Hold up your hands again. They are mirror images of each other. But you cannot perfectly superimpose one on the other. You can't fit your left hand into a right-handed glove. This property is called chirality. In the world of particles, a similar property exists called spin, or helicity. You can think of it like the rotation of a bullet fired from a rifle barrel. A particle moving through space can spin clockwise or counterclockwise relative to its direction of motion. We call these right-handed and left-handed particles. For decades, physicists assumed that the laws of nature were ambidextrous. If you took any physics experiment, and you ran its perfect mirror image, you should get a mirrored result. This principle was called parity conservation, and it seemed obviously true. Then came 1957. A brilliant and meticulous experimental physicist named Qianxing Wu decided to put this assumption to the test. She was one of the most respected scientists in the world, an expert in beta decay. She designed an experiment of legendary difficulty. She took a sample of the radioactive element cobalt-60, and, using powerful magnetic fields and cryogenic technology, cooled it down to just 1/100th of a degree above absolute zero. That's colder than deep space. Why? To get all the atomic nuclei to stop jiggling from heat and align their spins in the same direction, like tiny magnetic compass needles. Then she simply watched. She counted the electrons being spat out by beta decay. If parity was conserved, if nature was truly ambidextrous, the electrons should fly out in equal numbers both up and down relative to the nuclei's spin. The universe should not have a preferred direction. But that is not what she saw. Far more electrons flew out of one end than the other. The results were so shocking, so world-shattering, the team checked and rechecked for months, terrified of an error. But there was no error. The universe had a preference. Nature, at a fundamental level, can tell the difference between left and right. Parity was broken. The weak force, the only force neutrinos feel, is fundamentally left-handed. And here's the kicker, it turns out that every single neutrino ever created, observed, or detected in the entire history of science has been left-handed. Every antineutrino is right-handed. There are no right-handed neutrinos. The factory just doesn't make them. This is clue number 2 in our cosmic crime. A deep, baked-in asymmetry in the rules of reality itself. A tiny crack in the perfect mirror of the universe. And as we will see, through that crack, everything we know might have emerged. But the neutrino hadn't finished rewriting the physics books. A new mystery was brewing. Physicists had a very good model of the sun. They knew the nuclear reactions in its core and could calculate, with high precision, exactly how many neutrinos it should be sending our way. So, in the 1960s, a chemist named Ray Davis Jr. set out to count them. Because neutrinos ignore almost everything, he had to put his experiment deep underground, in the Homestake gold mine in South Dakota, to shield it from other cosmic particles. His trap was a gigantic 100,000-gallon tank full of perchloroethylene, basically, industrial dry-cleaning fluid. Every now and then, a solar neutrino would hit a chlorine atom and turn it into a radioactive argon atom. His job was to periodically flush the tank and, with incredible chemical precision, count the handful of argon atoms created. For 30 years, he ran the experiment. And for 30 years, his results were consistently, stubbornly wrong. He only ever found 1/3 of the neutrinos that the solar model predicted. This was the solar neutrino problem. And it created a war in the physics community. Was Ray Davis's incredibly difficult experiment wrong? Or was our entire understanding of the sun, the most important object in our sky, fundamentally flawed? The answer, it turned out, was neither. The problem was our understanding of the neutrino itself. A new generation of massive detectors came online. Super Kamio Candy in Japan, a breathtaking cavern filled with 50,000 tons of ultra-pure water and lined with 13,000 light detectors like giant, golden eyes. And the Sudbury Neutrino Observatory, SNO, in Canada, which used 1,000 tons of heavy water where the hydrogen is replaced by its heavier cousin, deuterium. These experiments confirmed Davis was right. There were too few of the type of neutrino the sun makes, the electron neutrino. But SNO could do something unique. It could also detect the other two types, or flavors, the muon neutrino and the tau neutrino. Think of them like vanilla, chocolate, and strawberry. The sun's recipe only makes vanilla. And when SNO tallied up all three flavors, the number was perfect. It matched the solar model exactly. The missing electron neutrinos hadn't vanished. They had changed their identity on the 8-minute journey from the sun to the Earth. They had morphed from vanilla into chocolate and strawberry. This shape-shifting phenomenon is called neutrino oscillation. And it was an absolute bombshell. According to the bizarre rules of quantum mechanics, for a particle to be able to change its identity over time, it must have mass. The standard model of particle physics, our glorious, tested-to-death blueprint of reality, had one firm entry in its ledger: neutrinos are massless. And the ledger was wrong. Our ghost, it turned out, was not weightless. It had mass. A whisper of a mass, millions of times lighter than even an electron, but it was not zero. The most fundamental description of our universe needed an upgrade. Our suspect was not just a thief and a rule breaker, it was a master of disguise. And this ability to change, this is directly linked to the crime of existence. Okay, let's stop and review the case file. We have a suspect, the neutrino. We know its methods. It's a left-handed ghost that feels only the weak force. We know it has an alias. It can change its flavor, which means it has mass. But what does any of this have to do with you? Why does a shape-shifting, left-handed ghost particle allow your solid, real hand to exist? Let's return to the scene of the ultimate crime, the first second of the Big Bang. The problem remains the same. The universe was born with a rule of perfect symmetry. For every quark, an antiquark. For every electron, a positron. 1 for 1. No exceptions. As the universe expanded and cooled, these pairs should have found each other and annihilated. 1 billion matter particles meeting 1 billion antimatter particles, leaving behind 1 billion photons of light and 0 particles. The universe should be a sea of light. For us to be here, for this planet to be here, for every galaxy and star to be here, that initial annihilation must have been imperfect. The cosmic scales must have been tipped. For every billion antimatter particles, there must have been 1,000,000,001 matter particles. After the cataclysm, only that one lonely survivor in 1,000,000,000 remained. That tiny remnant, that 1 in 1,000,000,000 rounding error, is everything. It's the entire material universe. You are made from the leftovers of the greatest cancellation in history. So, what could tip the scales? How do you create a universe with more stuff than anti-stuff? The great Soviet physicist Andrei Sakharov laid out the 3 conditions in 1967. Think of this as the recipe for existence. First, you need a process that can create the building blocks of matter, like protons and neutrons, called baryons. The Big Bang has that covered. Check. Second, you need this process to happen during a time of rapid change, when the universe is not in thermal equilibrium. The rapid cooling after the Big Bang works perfectly. Check. Third, and this is the crucial ingredient, you need a process that violates the symmetry between matter and antimatter. The process has to be biased. It has to favor producing matter over antimatter, even if only slightly. This is called CP violation. The C stands for charge conjugation, swapping a particle for its antiparticle. The P stands for parity, looking at its mirror image. If CP symmetry holds, a left-handed particle decaying should be identical to a right-handed antiparticle decaying in a mirror. But if CP is violated, they behave differently. The laws of physics are not perfectly symmetrical. Remember the weak force's left-handed bias? That was P violation. Physicists have found that the weak force also violates C symmetry. But when you combine them, for the most part, the CP symmetry holds. Almost. We found a tiny amount of CP violation in the behavior of other particles, called quarks. But it's not enough. Not nearly enough to explain our 1 in a billion survival. We need another, more powerful source of asymmetry. This leads us to the most elegant and audacious theory in the case, leptogenesis. Let's break down the word. Genesis means beginning. And lepto refers to the family of lightweight particles called leptons, which includes the electron and our favorite ghost, the neutrino. The beginning from neutrinos. Here's the theory. It postulates that in the searing furnace of the early universe, our familiar, lightweight neutrino had a partner. An unseen, ridiculously heavy sibling. Think of a seesaw. If you have a huge, heavy person on one side, the other side becomes incredibly light. This seesaw mechanism is our best explanation for why the neutrinos we see are so bafflingly lightweight, because their hypothetical partner is stupendously heavy. Okay, so we have this super heavy neutrino. In the early universe, it was unstable. It decayed. And here is the motive for the crime. What if its decay was biased? What if, due to a large amount of CP violation in the neutrino sector, this heavy neutrino decayed into slightly more leptons, like electrons, than it did anti-leptons? It's like a crooked casino dealer. For every 100 times the heavy neutrino decays, maybe 50.0000001% of the time it produces a lepton, and 49.9999999% of the time it produces an antilepton. An infinitesimally small cheat. This would have left the baby universe with a tiny surplus of leptons. More electrons than positrons. Now for the final masterstroke. At these insane temperatures, there was a bizarre quantum process in the Standard Model. Let's not worry about its scary name, Sphaleron, that acted like a cosmic currency exchange. This process wanted the books to be balanced between the lepton family and the baryon family, protons and neutrons. When it saw there was a surplus in the lepton bank account, it automatically converted some of that surplus into the baryon bank account. So, the slight excess of electrons became a slight excess of protons and neutrons. The building blocks of you. Then, as the universe cooled, 2 things happened. First, the currency exchange closed for business. The baryon number was locked in. Second, the great annihilation occurred. The billion particles met the billion antiparticles and vanished. But because the books were cooked from the start, that tiny, transferred surplus of baryons had no one to annihilate with. They were left over. That's the theory. A cheat that started with a heavy ghost particle cascaded down to create all the atoms in the cosmos. This is a stunningly beautiful story. It connects the smallest masses we've ever measured to the largest structure we can see. It makes perfect sense. But in science, sense isn't enough. We need a conviction. We need a smoking gun. How can we possibly prove a theory about something that happened in the first fraction of a second of time, involving a particle we can't even detect? We need a clue left behind in the modern universe. And there is one. One crucial piece of evidence that could validate the entire leptogenesis model. To understand it, we must ask the strangest question yet: is the neutrino its own antiparticle? For almost every other particle, the answer is a clear no. An electron has a negative charge. Its antiparticle, the positron, has a positive charge. They are different. A particle like this is called a Dirac particle. But the neutrino is electrically neutral, so there's no charge to tell it apart from an antineutrino. It's possible that the neutrino and the antineutrino are literally the exact same thing. A particle that is its own antiparticle is called a major nanoparticle, after the brilliant and mysterious physicist who proposed it. The leptogenesis theory strongly prefers the neutrino to be a major nanoparticle. So this is it. This is the key. Is there any experiment we could possibly run that could tell us if this ghost is its own reflection? Yes. It is one of the most difficult, important, and sought-after searches in all of modern physics. It's called neutrinoless double beta decay. The name is a mouthful, but the concept is pure elegance. We know that in very rare isotopes of elements like germanium or xenon, a nucleus can undergo double beta decay. Two neutrons simultaneously turn into two protons, emitting two electrons and, to balance the lepton books, two antineutrinos. This is rare, but it happens. We've seen it. But what if the neutrino is a major nanoparticle? What if the neutrino and the antineutrino are the same thing? Then think about what happens inside that nucleus. The two antineutrinos are created. But if they are their own antiparticles, they can meet and annihilate each other. They would cancel out before they ever leave the nucleus. So from the outside, all you would see are the two electrons flying out, and nothing else. No neutrinos. At all. A decay with no ghost escaping the scene. Finding this process would be the ultimate smoking gun. It would prove that lepton number, this fundamental quantity we thought was always conserved, can be violated. It would give us the single piece of evidence we need to believe that neutrinos could be responsible for our existence. Across the globe, in labs built deep under mountains of rock and ice to shield them from cosmic rays, massive experiments are searching for this one specific signature. Experiments with names like Legend, Camlanzen, Kuor, and EXO. They take tons of hyperpurified germanium crystals or liquid xenon, cool them to near absolute zero, and watch. They are looking for that one telltale spike on a graph, where the energy of the two outgoing electrons adds up perfectly to the total decay energy, proving nothing was stolen by invisible escapees. So far, they have found nothing. The silence is deafening. But with every passing year, the experiments get more sensitive, narrowing the hiding place of this elusive process. A single confirmed event could rewrite the first chapter of the universe. The hunt is on. Let's go back to your hand one last time. Feel its solidity, its warmth, its reality. Its existence was never guaranteed. It's the consequence of a cosmic imperfection. A lucky break in the fine print of the universe's laws. You are the product of a fundamental bias. A weak force that inexplicably favors left over right. A ghostly particle that refuses to be massless and insists on changing its disguise. And maybe, a profound and hidden asymmetry that allowed a heavy neutrino to cheat at the moment of creation, refusing to let the universe cancel itself into a void. We live in a cosmos built not on flawless perfection, but on the beautiful, reality-generating power of its flaws. The universe isn't a perfect crystal, it's a story born from a crack in the mirror. The audit isn't closed. The final evidence isn't in. But the case file points towards a stunning verdict: the most elusive, quietest, most reclusive particle we have ever discovered might just be the architect of everything you have ever seen, or touched, or loved. The near-nothing that ensured the universe would be filled with something. The ghost that made us real. This investigation is far from over. What if there's another, even stranger neutrino we haven't even talked about? A fourth ghost that doesn't even feel the weak force? The audit of reality continues. And while you're at it, you helped us crack this case today. Drop a comment below and tell me, what one concept from this entire audit blew your mind the most? Was it parity violation? Leptogenesis? I will be reading every single one. Finally, the universe is spilling its secrets every single day. Make sure you're here to hear them. Subscribe for your daily audit of reality, so you never miss another clue. You are the detective. This is your case.